professor in MIT. Now he's an assistant professor in the University of California, San Diego, in the mechanical engineering department.
This button on top.
Thank you very much.
Push it that
Can you
way.
hear me? Yeah. Yes. All right. So first, I would like to thank the organizers for inviting me. It's been a great day so far. We'll see for the next 45 minutes. I feel like a biologist because I have an acknowledgement. In fact, I have also acknowledgement of funding at the last slide. So what I will tell you about today is work in collaboration with two students, Gwyn Elfring at UCSD and Alison Burke, who's now a graduate student at Berkeley, and three collaborators, two at Harvard, Linda Turner and Howard Berg, experimentalists, and with a collaborator in France, Denis Martelot, who I know is watching this right now on the web, just to make fun of me. All right, so the outline is what I will do is I will spend a few minutes introducing you about what I call the nonlocal hydrodynamics, so basically the topic of hydrodynamic interactions in cell motility, when is it important, and what have people done so far in this field. And then I will talk about three specific topics, if I have time, that my group has worked on. One is the issue of attraction of swimming cells by solid surfaces. This is not a picture of an experiment, this is a drawing. The second topic is the issue of phase locking between cells which are swimming in close proximity. This is a picture of an experiment. These are human sperm cells. And then I will tell you about something which is a little less biological, a little more physical, which is can we use hydrodynamic attractions to swim? So to exploit the fact that objects interact hydrodynamically to make them swim. So first I will do a quick introduction, just have a few slides. So what I will talk about this talk is mostly about fluid mechanics. Okay, so of course there is some biology, but it's mostly where the question I'm addressing are fluid mechanics question. The world that we're focusing is what Purcell has called the life at low Reynolds numbers. So this is the sub-millimeter length scale. We're going to talk about swimming bacteria. We're going to talk about reproduction and swimming sperm cells. We're going to talk, I think, a little bit about ciliates, and there are other mini microorganisms which are exploiting fluid mechanics forces to move. So the two different ways you can think of how fluids exploit cells exploit fluid forces to move. So I'm not going to talk about crawling. Everything is a cell sitting in a viscous fluid and somehow deforming its shape so that it can move forward. The two ways the two canonical ways that this is done at the cellular level is prokaryotes. What they do is they have filaments, which are called flagella. Those are also called flagella, but they're of a different nature, but both are called flagella, so we use that name. Those filaments are essentially passive helical filaments that you rotate in a fluid. They're rotated by the motor, which is embedded inside the cell wall. And if you rotate such a chiral object in the viscous fluid, in general, that will push you in one direction. And that's how you do it. So this is a bundle of those filaments that are rotated in one way, and as a result, the cell moves forward. Eukaryotes, such as sperm cells, use also flagella, although these are completely different organelles. These are little muscles, if you will, and which are basically what it is it's a collection of polymeric filaments, microtubule doublets, which slide past each other, and because there are elastic constraints between those filaments, the sliding becomes bending. So you get bending waves which propagate essentially in the plane from the cell to the tip of the flagellum, and at the end, and as a result, the cell moves forward. Okay, so the actuation, this actuation is done by, it's a point actuation here at the boundary. Everything else is passive. Here the actuation is distributed along this filament. And so this is sort of the framework that we're going to consider here. We have small organisms which are actively dumping energy into the fluid, and as a result of their swimming, by the way, they're going to generate a net flow, which we're going to talk about, and Miming has talked a little bit about today as well. So hydrodynamic interactions, when is it important? There are three cases where it's important, and three cases where, by that I mean it's been recognized that it is important. One is interactions between flagella. So this is the case for cilia. So cilia are short flagella which are embedded into boundaries, and as a result of hydrodynamic interactions, as a result of the flow basically set up by, as one cilium is beating, it set up a flow field which is felt by the next cilium, etc., etc. As a result of those hydrodynamic interactions, those cilia beat in a coordinated fashion, and the waves that are propagating along those areas of cilia are called metachronal waves. I don't know if you can see it in the movie. right? But the cilia that are beating, and you're supposed to see here that they're beating in a coordinate fashion, so start beating together. Okay, so and that is solely due to hydrodynamic contractions. Second type, so these are the same type. The structure of those cilia are the same as the eukaryotic flagella that I showed in the previous slide. Another topic where hydrodynamic contraction is important is in bundling. So bundling is this phenomenon that as the bacteria is swimming forward, so imagine E. coli that's swimming forward, what you see here as a thick helix on the back is actually made of a small number, but more than one, helices. Yes?
Is it proven that it's a hydrodynamic interaction, or is it just estimated?
I don't know, what's the definition of proven, but it's as close to proven as I can think. I mean, it's been proven that, well, okay, let me erase the last sentence. With hydrodynamic interactions, you can get the same waves that you see in the experiments. If you have a mechanism, and I'll talk about this a little bit more. If you have a load-dependent mechanism that is generating the bending and the actuation for one cilium, the load-dependent mechanism, so there's a feedback between the fluid mechanics force, which are generated by N-1 on that particular cilium, that's enough to get waves. So that's this paper. KPNS paper 1990, group from Israel. Great paper, by the way. So, proven, I don't know whether it's been proven, but at least that's the sufficient ingredient to get.
So that's in 2 dimensions?
That's in 3 dimensions. These are filaments. Well, it's just a picture, that's a 2D picture, but these are filaments, not sheets. Does that answer your question? Okay. All right. So the question session will be fun. All right. So the second topic that I was about to tell you about is bonding. So when you look at a swimming cell, as a swimming bacterium, it has this bundle of flagella. What it does, and as you've seen 2 talks ago, is that this cell is going straight and then it reorients and then it moves straight and then it reorients and it moves straight. To do this reorientation, there's an unbundling and bundling phenomenon that takes place where the flagella, which are constituting this bundle, come apart and then come together. And they come apart, that reorients the cell in a somewhat random fashion, and they come back together, and then the cell moves forward for another second. And then you do it again, you do it again. The process by which those flagella here are coming apart and then coming again together is hydrodynamics. And so there are very interesting questions here about the coordination. How do you coordinate the movement between those N helices, given that they're basically passive objects which are driven only at the boundaries. And so this is a topic that has been investigated for a while, and this is a topic where hydrodynamic interactions is crucial. Another type, so I said that there are 3 types. One type was interactions within a cell between different flagella. Another type is interactions between a cell that's swimming in the boundary. So that leads in general to 2 things which are changing. One is it could change to it could lead to a change in the swimming kinematics. If you have a cell that swims one way in an infinite fluid on its own, then if you look at it in your wall, then something different could happen. This is a picture of an example of that, where you have E. coli cells, which if you take smooth swimming cells, these are cells which should not do this reorientation, that only swim straight, then far away they will be only swimming straight with some diffusion. Then if you actually put them near a surface, okay, so a few microns of a surface, then those cells, because of hydrodynamic contractions, now swim in circles. So that's an example where interactions with the wall gives you qualitatively new phenomenon, where now it's actually a confined swimming instead of being an infinite swimming. And the other thing that could happen is, of course, because friction increases near walls, the force distribution on the organism is changing because of this change in friction. So an example of this is an experiment that we've recently done. You can, if you were to grab on a cell, so what we've done is with human sperm cells, but you could do it with something else. You grab onto the cell with a tweezer to prevent the cell from moving. You need to apply a force to do this, right? And that's the force that if you let go, the will balance the drag of the cell that's swimming. And you can ask the question, well, how does this force, the force I need to apply to prevent the cell from swimming, change with the confinement and the distance to the wall? And there is a change. So the fact that the friction changes near the wall gives you a change in the force. Now the third type of hydrodynamic interactions is between cells. And this is the one that recently has been studied a lot. And so if you have N cells, you can have either a small number N or a large number N. The small number is typically people have done experiments or simulations where they look at 2 cells. So for example, these are computations for 2 E. coli-like bacteria which are swimming. And as they're swimming, they're getting closer together. We'll see later on why that's the case. And then when they're getting very close, then they're starting to spiral and get some instabilities. And there's been a lot of studies of that form. We'll talk about phase locking in a little bit. When the number of cells is very large, then there's been a significant amount of work recently on collective locomotion. And so people also refer to this sometimes as bacterial turbulence, because it looks like turbulence, but at a zero in this number. And what they find is that if you, and you've seen this in Ming's talk 2 talks ago, that if you have a suspension of swimming cells and you increase the density, and at some point, whether it's a sharp or continuous transition is still, I think, debated, but at some point when they're sufficiently dense, you get modes of locomotion which are qualitatively different than the modes of locomotion that you would have if you were to consider just one cell. Okay? So you get very intermittent behavior, you get vortex-like structure, you get jets, and the length scales and velocity scales which you get in those phenomena in these observations have nothing to do with the length scale of a single cell and the velocity scale, the swimming velocity scale of a single cell as well. So there's been a lot of work recently, and I'm not going to talk about this today. So what I will tell you about is 3 different topics. The first one is the issue of hydrodynamic or not attraction of cells by boundaries. So the question here is the following. Suppose I have cells, smooth swimming cells, and I put them in a confined environment. Okay, so I put them between 2 glass plates. And we can ask the question, well, what is the steady state distribution? Is it going to be uniformly distributed or not? Okay, and if it's not, then what's the physical mechanism? So that's the question we want to address here. The previous work on this question has been, the person who really asked this question was Rothschild in the Nature paper, where he's done an experiment with bull sperms, which are, I think, 300 microns, large sperm cells between vertical plates to get rid of gravity. And then he asked the question, well, where are the cells in steady state? And he gets this profile, which is something that's really flat and then it peaks at the wall. Recently, in the work in the group of my gram at Wisconsin, they've done some simulations where of collective locomotion. Actually, the picture that I showed here, right here from the same paper, they've asked the same question, and they say, well, as a function of the volume fraction, they find an appropriate way, what's the steady state distribution? And at low volume fraction, they get this red dashed curve here, which is basically the same idea, where it's flat in the center and then it peaks at the wall. So there's a strong attraction in steady state, if you will, of the cell distribution by the wall. So that's what we want to think about. So in collaboration with Howard Berg, we've done an experiment. Alison Berg did the experiment over in Howard's lab. So the experiment is the following. You take a suspension of smooth swimming E. coli cells. So by smooth swimming, I mean they do not do this run and tumble. They're only running and diffusing. And you put them in a fluid that is density matched. And then you take this solution and you squeeze this between 2 glass plates, which have been treated such that there is no adhesion, and the interactions between swimming cells and the boundaries are as simple as possible. And then you basically make slices and you image where the swimming cells are. You get pictures like this. You count the cells which are swimming, and it turns out they're all swimming in the plane. We'll see why. And then you count and then you report. And then that's what you get. So there are 2 parameters. We do experiments where we vary the thickness between the distance between those 2 glass plates, and we can also vary the size of the cell population. So you get profiles like this that are, if not constant, close to constant in the center, and then peaks significantly at the wall, and this is well reproducible. So we consider this to be steady state, or as close to steady state as we can. So that's what we want to think about. So why would the cells, as they swim, be attracted by the wall? So it's a hydrodynamic effect. So what do I mean by this? Well, let's look at the flow created by a single cell. So the flow created by the single cell is as Ming explained to you, is a force dipole. So there's no net force. But there's a first moment that is non-zero because, so this is supposed to be a picture of E. coli. As the flagella is rotating, this flagella is pushing fluid in this direction to the right. And of course, the cell is moving, so it's also, with the body of the cell, is pushing fluid to the left. So there's a first moment that is non-zero. And so far away from the cell, you can think of it as a disturbance to the flow. If the cell was not here, the flow would be quiescent. But if you put the cell, there's a net flow that's created. This is disturbance. And the disturbance is, to a very good approximation, that due to a force dipole. So that you can think of the cell far away, at least further away than the size of the cell, as this dipole, this red dipole. Now the flow field that is induced by this dipole is divergent, is going away from the cell in the direction in which it's swimming. So it's pushing fluid on this back, it's pushing fluid ahead of it. But then by mass conservation, it has to attract fluid on the other 2 directions. And the cell is axisymmetric. If you average the cell over 1 period of oscillation, you get an axisymmetric geometry. So the cell, as it swims, must attract fluid on the side. So it's this side and this side. Okay. So that means that if you have a little particle here, then as the cell is swimming, it would go towards the particle. Okay, and this is why if you have two cells which are swimming, they're getting close together because cell A is pulling cell B towards it, and cell B is pulling cell A, so as they're swimming, they're going together. So now, if you have the same thing, and if you think of this near a wall, well, this flow field has to be modified to account for the fact that there's a surface here, a no-slip surface, and basically what happens is that the cell cannot attract the wall because the wall is stuck, and so itself the cell will go towards the wall so that in the frame of the cell, this mass conservation argument is still satisfied. In the frame of the cell, you still have the same mass flux going through to replenish whatever fluid you're pushing in both directions. Okay? So there's an attraction. There's a hydrodynamic attraction. For those of you who know about images, hydrodynamics, you can think of this in terms of images. If you have a forced dipole, if you have a surface which is a no-slip surface, the net flow, the total flow, which is the superposition of this dipole plus the fact that there's a surface, can be thought of as replacing the surface by a bunch of images which are located on the other side, just like we do in electrostatics. The image system is complicated because the boundary condition is a complex three-dimensional boundary condition. You have to satisfy that three vectors are zero. It's no slip. You have a question?
The effect isn't cancelled by the repulsion experienced by things that are swimming straight through the wall. Those are going to be repelled, right?
Yes, but the answer is no. It's not cancelled. It's not. So that's.
And there's a way of understanding that why it's not.
Well, that's how I like to understand it, but I don't really know what else to tell you about that particular question.
But close to the wall, there won't be any perpendicular tensile cells because they will tend to be parallel, right?
Correct. So I'm thinking of this as the first effect of the wall. I'm far from the wall. What's the first effect of the wall? I'm far from it, say further away than one body length, and that's the first effect of the wall. Of course, when I'm getting closer, it's more complicated because when I'm getting closer, the cell is not a force dipole anymore. The cell is a continuous body with a force distribution, and then it's more complicated.
Why is it Bernoulli effect, where if you have flowing fluid, it's just lower pressure, so it'll be just attracted to the wall because there's less pressure there?
So the question about Bernoulli effect. So Bernoulli is a high Reynolds number effect. It's an inertial effect. It's got the density of the fluid. There's no inertia. It's a zero Reynolds number. Okay. It's purely viscous flows. Okay. So basically, what I was about to tell you was that if you have those images, the effect of the wall is the same thing as just those images. They're complicated. There's another force dipole. There's a force quadrupole. There are source quadrupoles. But anyway, you don't need to know the details. What you need to know is that you know those images analytically, so you can then calculate the effect of those images back on the original position of the original dipole, and then you get a flow that's going down, velocity that's going down. So that's the attraction. There's an even simpler way to think about this is that if you were lucky that the surface was not a no-slip surface, but a free surface, okay, like an interface between a fluid and a gas or air, then the image system is very simple. It's the same singularity. Whatever singularity you have in the fluid, you just need to put the exact same one on the other side, right? And that's a ghost or image cell on the other side. And as those two cells are swimming, they're going to be attracted to each other, and so the wall effectively attracts it. Okay, so that's the hydrodynamic. The attraction by the wall is hydrodynamics. Now, the problem with this idea is that it's true. What I told you is true. The cell is swimming parallel to the wall. But of course, if you're looking at this, if you're changing the orientation of the cell, this attractive flow field towards the cell is only true on the side, but then on the front, the flow field is actually going in the other direction. So the cell has an angle with the surface which is not 90 degrees. Okay, if you call this angle theta, this attraction becomes a repulsion. Okay, so that's a little bit of a problem. You can calculate that analytically, and you can show that when the angle is such that cosine is 1 over square root of 3, you switch from an attraction to repulsion. Not only that, if you take a suspension of cells, and they're all at the same distance from the wall, h is the same for all of them, but they sample all the different orientations, so they're uniformly distributed in orientation, the net effect of the wall is 0. Okay? The net effect of the wall is 0. So if you want to really have an effect on the wall, you need to somehow find a way to bias the orientation of those cells as they're swimming. Otherwise, the wall doesn't really do anything to you. And so what we've argued in our paper is that hydrodynamics also does this to you. And the reason why it does this to you is the following. It's actually simple when you think about it. The reason why it does this to you is I told that you think of a wall as the effect of the wall is the same as removing the wall and putting image on the other side, just like you do in electrostatics. Now, those images here, you sum them all up, that gives you velocity field, which you can calculate everywhere. And then at the position of this dipole, in general, this velocity field will have a velocity, which is this thing, this blue arrow that I plotted here. But also, in general, it will have a non-zero velocity gradient. And if you have a body in a non-zero velocity gradient, as we know, well, this thing will rotate. And so we have to actually ask the question, well, the effect of the wall not only leads to an attraction or repulsion, depending on the orientation, but also will lead to a change of the orientation. And that's what we have to calculate. And so it turns out we're lucky because that will give us what we want. So if you think of the cell as a prolet spheroid, which is a good approximation, if you call E the swimming direction, it will rotate, and the rotation rate omega will be related to the velocity gradients of the velocity field due to all those images. And what would omega be? Well, omega would be, one part of it will be the vorticity. Okay, so as we know from fluid mechanics, the vorticity is twice the local rotational speed of fluid elements. So if you have a sphere in a body, in a fluid that has vorticity, this field will rotate at a rate which is 1/2. So that's one piece. And the second piece is for objects which are elongated. So gamma is the aspect ratio and gamma is more than 1. Then objects which are elongated, even if they were in a flow that has no vorticity, in a potential flow, they will rotate because basically the simplest potential flow you can think of is a flow that is straining. And in a straining flow, an elongated body will always align with the principal axis of straining. Okay, even though there's no vorticity in this flow, you will still get rotation. You will still get velocities of different parts of the body that are different. And so basically, if you know the velocity field, from the images, you can calculate the velocity gradient. The symmetric part goes in this rate of strain. The anti-symmetric part goes in the vector vorticity. So you can actually calculate this analytically. And then you can ask the question, well, which way does it go? So it turns out that this rotation rate, this thing in brackets here is positive, so we don't need to worry about it. It's the same sign as the dipole strength, minus sign and then cosine sign. So that means that for all our cells, the dipole strength is positive. Those cells are pushing the fluid, and we'll come back to that. And so therefore the sign is the same as minus cosine sign. When the angle is between 0 and pi over 2, this is positive, so that gives you an omega which is negative. So as the cell is swimming towards the wall, it will be reoriented parallel to the wall. The omega goes in this direction. And if the cell is swimming away from the wall, you flip the sign of omega because now the angle is above pi over 2, and now the rotation rate will be in this direction. So both give you orientation as they're swimming parallel to the wall. So that's the mechanism you need, if you will, to bias the orientation of the cell, so that eventually the only stable configuration is what the cells are swimming in the plane. And that's why when we do our measurements, we see the cells swimming in circles in the plane. Now, one thing that's important that I won't mention, but I'm going to tell you right now, is that if you flip the sign of the dipole, if the cell, instead of pushing the fluid away from it as it's swimming, pulls the fluid on it, and so these are the case for some eukaryotes, some algae are doing this. So essentially, instead of pushing constantly against the fluid and going the other way, what they're doing is, as a rope, they're constantly pulling up the fluid. Those cells will have everything will be reversed. So the only stable configuration for those cells will not be swimming parallel to the wall, but will be swimming perpendicular to the wall. So those cells will eventually all crash into the wall. So they will be attracted to the wall, but for completely different physics, because it's not hydrodynamics. Hydrodynamics rotate them and then just crash into it. All right. So once you have this, then you can write down what the expected distribution of the cell would be once the cells over time. If you wait basically 1 over a time scale, which is 1 over this rotation rate, then the cells are going to be swimming parallel, and then they will be attracted to the nearest wall, and that's what we want. So the equation, the sort of a simple model, is a balance between diffusion perpendicular to the wall and attraction by this attracting velocity field from the nearest surface. Simple model is just summing up the two solutions for 2 infinite walls. These are the two solutions I gave you earlier, and you get a function that looks like this. It's an exponential of 1 over z, and the only parameter really that comes into play is a length scale. And it's a typical length scale, over which this profile decays. This is the fit from our theory to the data. This length scale in our experiments is between 20 and 60 microns. And what's interesting about this length scale is that if you were so you do those measurements, you measure length scale, and if you know the viscosity and you know the diffusion, then you can figure out what the dipole strength is. And dipole strength is the size of the cell body times. It's basically the first moment of the force distribution. So you can just by doing those measurements, by taking pictures, you can say something about the force, the typical force that those cells are applying to the fluid. So again, you know what L is because you measure it. You know what D and the viscosity is. So therefore, you can figure out what the dipole is. And since you know that the dipole is a typical force, because it's typical force F, times the typical distance between whatever is producing the thrust and whatever is filling the drive, which is about a micron, which is about the size of the cell, you can figure out, only by doing those measurements, by taking pictures, you can figure out something about the force. And so fitting our experiments to the model gives us a force which is in the range of 1 to 0.1 piconewton, which agrees well with what people have actually measured, doing actual force measurements. Okay, so that's all I wanted to tell you about attraction by the walls. I think I'm going extremely slow. So I might have to skip number 3, but that's okay. So the second topic I'm going to tell you about is the issue of phase locking between cells and swimming. So there have been a number of experiments that have, not very quantitatively, but at least say in their paper that they've noticed that as swimming sperm cells are in close proximity, 2 or more, they tend to sort of move relative to each other until they're in the phase locking scenario. So this is not to say that the cells are exactly phase locked. If you were to take the 2 cell bodies with a flagella on the back, those flagella are not exactly between in coordination. But at least because they have this additional degree of freedom that this guy can move ahead a little bit, or this guy can move behind a little bit, then they can change the relative position so that the flagella appear to be phase locked. Okay? Just like it is here. You see that clearly those 2 guys are not at the same position, but the flagella yet are, right? So they're not exactly phase locked, but they appear to be phase locked. So the question I'm going to ask here is the following. To get this, does it require an active feedback between for example, the fluid mechanic force, the hydrodynamic flow that are created by the first cell, say cell A, on whatever is doing the force generation inside cell B, okay, like you would have in cilia. In cilia, because those flagella are stuck to the wall, in order to actually coordinate, you need to say something about whatever is doing the force generation inside each cilium. You need to have a load-dependent force generation to get coordination. You need that. So does it require this just like you need for cilia, or can you, because you have an additional degree of freedom that the cilia do not have, that is that those cells are able to, one cell can go faster than another, etc., can you purely passively, purely using just hydrodynamics, so prescribing the shape, the flagella shape, can you purely passively change your relative position and phase lock only from passive hydrodynamic interactions? That's the question I'm going to ask. All right. So the answer is yes. So the model we're using we're using a 2-dimensional model. These are 2 swimming sheets. So we have this is a model that's been used a lot for a number of low Reynolds number problems. What we have is we have 2 sheets which are sending traveling wave. They're parallel to each other, and they're sending traveling wave to the right of tangential deformation. Okay, just like you see for eukaryotic flagella, and as a result, they're both swimming to the left. They have a phase difference, phi, so the top one is ahead of the second one by phase phi, and as a result, the velocity are going to be a little bit different. And so there are 2 problems we can really. So when phi is 0, by the way, this is the configuration. So these are when the 2 waves are exactly in synchrony, and then phi equals phi is where they're exactly out of phase with each other. Okay, so that's what I mean by the phase. So there are 2 things we can ask. We can say, well, suppose we prevent the cells from moving past each other, so we set this velocity, this relative velocity here. Oh, my laser pointer is dead. I guess I shouldn't look to check, right? Okay, so if you were to set, if someone has a laser pointer, I wouldn't mind borrowing it. So if we set the relative velocity between those 2 sheets to 0, then in general there'll be a force, there'll be a hydrodynamic force. I'm sorry? Oh, there's a real. Oh, okay. Perfect. Thank you very much. So if you set, oh, nice, great. So if you set the relative velocity to 0, then in general there'll be a force, there'll be a hydrodynamic force which will either act to separate, to increase the phase difference, or to decrease the phase difference. We can calculate that force. Okay. But that's one type of problem you can ask, and it turns out all the physics is already there, because if the force is such that the phase increased, then that means that this situation when the phase is 0 is unstable, and if it actually decreases the phase, then that means that it's stable. And the other problem that you can solve is you say, well, if now they're both free to swim, then in general you can calculate this velocity, and the phase will evolve according to, of course, the differential equation says that the rate of change of the phase is the velocity, or proportional to the velocity. So you can solve those 2 problems, but all the physics is really included in this first problem. So the first thing we can do is we can already say something about cases where we know no phase locking is ever possible. So we're going to consider cells with flagellar waveforms, right? So really all discussion will be about these waveforms. It turns out it's all a question of geometry. We already are going to consider waveforms which are, as the cell is swimming, are right-left symmetric. If you don't do this, then really you cannot even do a 2D model, because that means that the cell would actually be swimming in circles, right? Because of this asymmetry And so this actually turns out to be very complicated. So we're going to consider in all this stuff that the cells are they're swimming straight, and the waveform is what I call right-left symmetric, right? Which actually on this picture will mean that it's top bottom symmetric. What we're going to consider here is that in addition to these geometrical constraints, we're going to consider waveforms which are also front-back symmetric, okay, like a sine wave. Okay, well, so what that means is that I can take a mirror image symmetry of this waveform and I get something that looks the same. Okay, so when you do this, what you see is that let's consider a configuration where they're both swimming at the same speed. There's a phase, so the pink is ahead by a phase. The force here is stabilizing. I can consider one setup where I'll get the exact same waveform. Now the phase becomes minus. I just did a mirror image symmetry. I can do another one where I do this way, right? So my sine wave, the one that's on top is now at the bottom, but I get the same geometry. So this is a problem that I can think about. And then what I can also do is I can take that problem and I can apply kinematic reversibility. For that problem, I have a wave that travels to the right. The swimming is to the left. If I flip the direction in which the wave is traveling, everything is flipping sign because these are Lorentz number, everything is linear. So if I flip the sign of the wave, now the swimming that was to the left for that problem becomes to the right. The force which was stabilizing now becomes destabilizing. Right? The phase remains the same. Now if I compare those two problems, okay, one is one that I obtained by mirror image symmetry, and the second one I did one mirror image symmetry like this, and then I did kinematic reversibility. Those two problems are the exact same. Okay, the phase has the same sign. Both have velocities in the wave that goes to the left. The swimming occurs to the right. But you can see that the force here is, this one is stabilizing, this one is destabilizing. And of course, those two problems have to be the same. And so therefore, the force has to be zero. There is never going to be any phase locking. If you can do this, that means if you have a waveform where you can do those two symmetries, then there's no phase locking. So if you take two sine waves, two symmetries that have exact sine wave, or any geometry that looks like a sine wave, there will never phase lock, ever. So you need to break the symmetry. You need to break the symmetry between the front and the back of the cell. So in that case, when you break the symmetry, so we have waveform now which are asymmetric, right? So there's a small slope on the long time, and then there's a large slope on a very short amount of the wave. If you break the symmetry, you cannot do this mirror image symmetry we have on the right. You can only do the one we've done here. And if you do this, then you flip the sign of the phase. You also flip the sign of the force, and so that tells you that the force is an odd function of the phase, which is what you need to say something about stability or instability of the fixed point, basically. All right, so we can actually solve this problem. We do this in lubrication limit where the distance, which we call h is a function, which is as a function of x being this direction, is much smaller than the wavelength, and it turns out that the math then is much easier. What we have a function of a waveform that we're going to keep arbitrary for the moment. It's a function a. That's something that's really the only function you need to describe the waveform. It's arbitrary. And then when you can solve this, and I don't give you the details, but that's the solution. So you get a force which is an integral over one wavelength of this formula. And what you see with this formula is that if the phase is zero, so if the two cells are in phase, like this, then I2 and I3 are moments of h. This thing becomes zero, the force is zero. So your two cells, if you start with a configuration that are already in phase, they won't evolve, they will stay there. It's a fixed point. And it's the same thing for pi. If you take the completely out of phase scenario, which is this one, it's also a fixed point. So they won't evolve. Now the question, of course, is, are those fixed points stable or unstable? Okay, because if it's unstable, then you won't see it. So what you can do is you can take this force, you can then say, well, I'm going to assume that the phase is close to either zero with a small perturbation phi prime, or pi with a small perturbation phi prime, and then I can calculate the force near that. What you get is we expected the force to be an odd power of phi prime, so we get that it's actually cubic. And we get two formulae. What I really want you to notice is that those two formulae are exactly the same. This is the force near in phase, this is the force near out of phase. They're exactly the same, except they have a different sign. Okay. So what that says is that if one configuration is stable, the other one will be unstable, and vice versa. Automatically, we get that in that formula. So specifically, if you give me a function a which describes the geometry of your flagellum, then I can calculate this integral. It's only a function of the geometry. It's an integral over a wavelength of a times the cube of the derivative. If this thing is negative, then I know already that this negative, there's a minus sign that becomes plus. This point here will be stable. This point here will be unstable. If you flip the sign of the waveform, and you give me now a waveform A for which this is positive, then I will flip the sign of stability. The in phase will be unstable, and the out of phase will be stable. And if you give me a waveform for which this interval is 0, then nothing happens. There's never any phase locking, which is the case we had with our sine wave. Okay? So to summarize, it's only a function of the geometry. You give me a waveform, I can calculate over one wavelength what this interval is, and depending on the sign, I can tell you whether phase locking will occur. It will always occur, but it will either occur in a situation where they're in phase or where they're out of phase. Now, Taylor said that the swimmers are swimming in phase in his paper in 51 because that's where they spend the least amount of energy. And it's true, you can calculate the amount of energy that's dissipated in the fluid between those two sheets, and you find that in phase is always giving you less energy. So this is a local minimum, this is a local maximum, so you're spending always more energy when to doing out of phase and in phase. But that doesn't mean that that's where you go. And in fact, I've given you a formula for the force that shows that you can actually have a situation where you pick a specific wave geometry for the waveform where the stable scenario is the out of phase, even though it's a maximum of energy. Just maybe 2 more slides. So you can then solve the problem dynamically. So you now remove the constraint that the two sheets do not move past each other. You're now putting a constraint that the force is free, and they will move such that this force that you're applying is going to be balanced by drag on them. And what you find is a complicated nonlinear ODE, which is just saying that the phase is basically evolving according to what the force would calculate before. You can integrate that numerically, and this is what you get. So I'm going to start by a configuration where those two sheets have a phase difference of pi over 2. If I get a waveform, a geometry which is a pure sine wave, then nothing happens. Okay, that's because of the symmetries I told you before. If I now break the front-back symmetry, I can break it. Either I have a basically mostly a cell that has an increasing amplitude, that's this blue line. Then I get a situation where I told you before, where the in phase is stable, and numerically I get that the phase is going to 0. And if I now break the symmetry the other way, where instead of having mostly an increasing amplitude, this waveform has a decreasing amplitude, then actually the stable point is the out of phase. Okay, so the system will evolve into a situation that's where it's dynamically stable, even though that's where it spends the most amount of energy dissipated into the fluid. So basically, the punchline is that it's all geometry, and unless you're really unlucky that the waveform is too symmetric, then hydrodynamic forces would always lead you to this apparent phase locking. So one swimmer will sort of go faster than the other one until they reach a position where they phase lock. But where you end up is only a function of the geometry. And you might end up in a situation where you actually spend the most amount of energy there, okay, dynamically. Just to show you that the stable point, if you take a waveform for which the stable point 0 is a stable point in phase, actually this should not be this figure. This looks like out of phase. It should be the other one. That it's the only stable point. So wherever you start between minus pi and pi as initial condition, you always end up on that point. So that's the only stable point. So I don't have time for this. I'm sorry. I just still want to put my conclusion slide though, because I want to show you pictures of people who worked on this. So I have some references here, and the work on attraction of cell by walls was done by Alison Burke, who's now at Berkeley, in collaboration with Ida Turner at the Rowland Institute and Howard Berg at Harvard. And the work on the phase locking between swimming sheets was done by Gwyn Elfring, probably listening to music as well. And the funding, Gwyn is supported by the nursing from Canada, and I'm auditioning funding from the NSF. And I'll be happy to take any question. Thank you for your attention.
I got the part where you showed why the first part, why it likes to swim in the same plane. But I finally missed how you got it to actually attract the side walls. In other words, how you got that function.
Well, once all the cells, so you are okay with the fact that the cells, even though they were starting initially by some orientation which could be completely, that it would end up swimming parallel.
Yeah, I got that.
Well, but then whatever is the nearest wall, right? So there are two planes. Whatever is the nearest wall is going to attract them hydrodynamically. This was the argument. My first argument about the cell as a disturbance is like a dipole. The dipole is attracted to the wall, just like two cells which are swimming near each other are attracted to each other. So in that case, the dipole argument is fine. The only issue is that you have to be careful with the orientation. And if somehow, basically, let's do the following. If you are not,
So it says that I didn't maybe this doesn't include it. So now if there's an attractive force. So
It's not really, I wouldn't say it's really a force. There's a flow, there's a low-induced flow that just pulls you down to the
Right, so
surface.
then it starts to move. So that is the now it has a vertical motion is where you get.
So it's as it's swimming, it's swimming in a plane, so it's swimming sort of parallel to the surface. As it does this, it's being attracted to the wall.
And so that is not considered a vertical component.
So that's what I call my vertical component. That's what I call my U-perp. That's my velocity component of the swimming kinematics, which is going towards whatever the nearest wall is.
And I thought you said that
the discussion is over.
held by the boundary. Say any velocity component in this direction.
Yeah, the next stop is 15 minutes.
No, what I'm saying is, if there was no boundary in the cell, which is say in this horizontal plane, it would go straight. If there is a boundary, just because of the presence of the boundary, provided the cell is going in this horizontal direction parallel to the plane, it will also be attracted to the wall. This is what hydrodynamics is telling you. This is all I'm saying.
Okay, so in your synchronization problem, you work at prescribed shape.
Correct. It's crucial, actually. I mean, it's not crucial, but this is the assumption. We don't do any assumption of how whatever is generating the force, they're doing this at fixed kinematics. Yes.
Okay, yeah, but really nature of the shape is not prescribed.
Correct. What's prescribed is the internal force generation.
Right.
Correct.
So how does that could affect the result? Or
Well, we haven't considered this. It's true. So basically, what you're saying is that the shape of the flagellum is not something that the cell is applying. The shape of the flagellum is a balance between the internal distribution of moments, basically along the axonym, and then whatever is the passive elastic resistance and the flow.
Right.
And of course, the real problem is to prescribe, even in a non-load dependent force generation, you prescribe the load and then you solve the problem. We haven't done this. We've done the sort of, in some sense, the even simpler, where we say, well, the shape is whatever it is, just like Taylor. The shape is fixed. Of course, it's not the real biological problem, but only with that you can still get, that's enough to get phase locking. Whether it's the real problem or not, it's of course a good question, and I don't know the answer to that because we haven't done that problem. Green is actually doing that problem now, but not for sheets, but for filaments, which is of course the new geometry, because there's another problem here. It's a two-dimensional problem, right? So we want to do the real problem, but not for 2 dimensions, but in 3 dimensions. So he has now, using a framework similar to the papers by Frank Uniker and Celeste Camille. I think you actually were an author on this paper, yes? So you must know. So using this framework, we actually are doing the real biological problem. But
okay, that's what I had in mind. Actually. Okay.
Exactly. So we're doing it.
So Eric,
Yes.
I don't know if this is,
I
but
can hear you.
so I actually have a question about a thing you briefly mentioned. So the disturbance that it makes free swimming is a dipole, but in what you talked about, where if you grab it with a tweezer,
Yes. Then it's not a dipole
it is
anymore.
not a dipole.
It's not a dipole
So
anymore.
can you really use the tweezer experiment to gauge the swimming when it's?
Oh no, but so first of all, the tweezer experiment, there was only like half a slide on it, right?
Yeah.
Okay. No. I just want to make sure that I didn't. Okay, that it was clear. The force is not going to be the same because the resistance to the flow resistance is not going to be the same. The cell is not swimming, of course. But basically, if you ask the question of how did, at least as far as I know, how did people measure propulsive force? That's what I think that they're doing. They've done this with bacteria. They've done this with algae. And it makes sense. Physically, you measure something that if you let go, will be balanced by a drag. But the truth is that as you let go, the force is not going to be the same.
Right.
That's right. So the force, what you're saying is that as you let go, the force is not going to be the same. And I agree with you, but that's what we measure. No, the force is zero. Of course, the net force will be zero. No, but what he's saying is that if you measure F, and then you balance F by drag, viscous times U, is U such that U equals F over this, or is it different? That's basically what you're saying. So.
Okay, so we've got time for one more question.
Yeah, Eric, did you assume that you have a sheet instead of a filament?
Yes. This is Taylor's model, 1951.
Okay, but wouldn't you then have a two-dimensional, which is very different dynamics than a three-dimensional?
Correct. So then
the
yes,
velocity would decay very differently.
Correct. So there have been some computations already in 2 dimensions that show that the people who've seen experiments with sperm cells happen the same way. There's a recent 2008 peer paper in 2D. So they show the same thing. They show that the cells sort of take advantage of this relative degree of freedom that cilia don't have to actually face up. And so we thought, okay, well, that's probably where enough of the physics is.
Okay, so let's thank the speaker again. So it's time for physicists to talk again. So Simon Nonlocal, he is from Princeton right now. His PhD is from Brandeis, and then he did postdocs all over the world: Florence, Dresden, and now Princeton.